So I turn the recording back on.
Okay.
I would like to just make sure that you're with, the current version of Easy Roll, which, you're going to have to use for the best performance with your current firmware. Advanced Dialogue Network Services, and we've discussed Discover. And we can discover our modules. We've done Select All, and we've made backups. Auto config will not apply to your modules. Actually, auto config with this software only applies to our other product, the AI2 product. A few more items about this tab. Number one, you kind of see up here, lock a network and unlock a network. What these features do is, one, you would select a specific network. We're working with the 185 network. And now we have our modules. We can select lock the network. Notice how we have a gray unlocked padlock right now. I say lock the network. These will now turn yellow and lock, indicating the network is locked. What this means is the network is locked out of two things. Number one, you cannot perform auto configure anymore. Number two, you cannot manually change IP addresses. So it locks that out. What will still work is the full functionality of your system and auto replace. What this is really good for is it prevents when someone has to perform auto replace, it keeps them from accidentally performing auto configure and messing up the conveyor. If you need to do some changes or change IP addresses, simply unlock the network. And now it's unlocked back to the way it was. A lot of our customers will lock their networks. They usually wait till after they're done making all their settings changes and things like that, and then they'll lock it up. Also, if you need to change firmware, one, you have to perform a discover. Two, you could pick a single module, or you could pick all modules. Select upgrade. Notice how it is a tab, but to get it fully populated correctly, you have to go to Network Services and perform Discover. Next, you would do Browse. And then, of course, browse to wherever you have your current firmware. So here you can see all the different revisions. 1, 3, and 4 were all the early years. And then version 5 was when we first started ODVA firmware. And then you would select your firmware, open, and then you can upload all at one time. So if you had 100 modules, you can upload the firmware to all 100 modules at the same time. When you upgrade firmware, number one, if you are connected to a PLC, you will lose temporary connection. One, because the processor will suspend performance to perform the upgrade, then it'll reset, and then it'll become available for PLC connection again. So you will lose temporary connection to a PLC. The control port tab, that would be the same as control ports here. And this is where the inputs, accumulation, pin 3, in-feed discharge, pin 4, you can invert those signals if needed. So if you plug in a wake-up eye and right away the control port LED is green and the zone starts running but the sensor is clear, you would come here and invert the signal, and that would correct it.
Okay.
The output by default is on when the sensor is blocked. You could invert it to be on when the sensor is clear, or to be on whenever the motor is running. You have some workstation features. Accumulate on sensor trigger for upstream and downstream zone. The way these work is you're at a workstation. So you have your zone set to accumulate. Operator loads, unloads a box. It's time to release it. Well, they would either have to press and hold a button or a foot switch until the load completely clears the eye, then release it. Because if you say accumulate and the eye is blocked, the motor will stop. So to help with not having to push and hold a button 2,000-3,000 times a day, this feature, what it'll do is when it's time to release the load, just press the button one time. The load will completely release. The next load arrives and shows up. So again, this is a workstation feature. And then if you have a lane full photo eye, by default, it's instantly blocked, instantly cleared, and acts as a confirmation signal to the last zone. If you decide to use it as a lane full interface instead of just a lane full, what that means is now you can add block and clear times like a regular photo eye. So it has to be blocked for 2 seconds to be considered blocked or full. Then once it clears, it has to be cleared for 5 seconds before you can start releasing again. So you have your options. And the reason you have last and first module is because of the ability to have a reversing conveyor. And then these two options here are the ones I was discussing a little bit yesterday. The control ports by default are for interlocking. But if you're not using a control port for interlocking, you could say enable the PLC to control that control port. And now what you've done, because I selected both of them, I've given the PLC 4 spare inputs and 2 spare outputs. And if you have a lot of cards with a lot of spare ports, that is a whole lot of spare remote I/O. You don't have to go purchase Allen Bradley. It's been a while since I've done projects. Was it like the 1492 Flex IO or 1794, something like that? And so you have to buy the IO module. Then you have to buy the Ethernet module to connect to that IO module. You got to buy an enclosure. You got to pay someone to build it and wire it, install it. With our card, it's already there. All you need is one of those little SC kits, and you can easily wire all your IO to those ports.
So that's just like telling the module PLC mode instead of CPA mode in a way.
Yes, in a way. The module will still perform ZPA and will still move the loads automatically. So that part's still intact, but this just gives you the option of using an unused port for spare IO. Special services. If you replace a motor, notice how here on this motor it says runtime 3 minutes. I could clear it. I put in a brand new motor and I can clear the runtime. Now it's 0. So this is a way to kind of track motor time. I find it a little strange that with this software and this one, it does still track time. We go to motors and see operating time. But once we went to the new product, they realized it was better, although they still track time, it's better to track on-off cycles. Because when we do motor testing and lifetime testing, It's about on-off cycles with a load, not can we turn it on? How long does it run? It's on, off, on, off. It's under load, being stressed, being fully tested. And so they went that route with the newer product.
Okay.
This motor slave thing, if I go, because this module you can see here is configured with one sensor and two motors. Because my modules have current firmware, this is an extra option. This is a way for when this is sometimes these two motors are underneath one belt because it's a heavy load, or maybe it's on an incline or decline. And there's a special way to control these motors, and that's by using the firmware and allowing the firmware to select all the settings. And that gives you your best performance. That's not available with that older firmware. So this is one of the things, touch and go. This isn't available with that older firmware. Flex zone. We talked about this yesterday in the documentation when we're talking. Notice how it does a little discover again. But here, flex zone lets you know that it is either all modules or no modules. For the new software, you actually click on the network itself because it is a network setting, and it's enabled or disabled on all modules. So this is a network setting. 50 milliseconds is usually a good default time. Sometimes, depending on the size of your packages or the length of your zone, you may want to decrease this. Your sensors, this is where you can invert sensor signals if necessary. Same way here, sensors. So it's all the same information in the newer version of the software. It's just not located, it's no longer in an advanced dialog. It's right on these main tabs.
Gotcha.
Okay, let's so that'll kind of wrap things up for the easy roll side. I'm sure once you start getting into adjusting settings and working with your system, you'll probably have more questions, which we'll tackle at that time. But for now, we've kind of touched on all the basics and what all the settings will do.
Okay.
I'm going to shrink this one and close the plus for now.
Gotcha.
And we will start with the developer's guide. So this is all the PLC connectivity information.
Okay.
Network architecture. This page basically discusses the modules and the main types of communication protocols. Ethernet IP, Modbus TCP, and Profinet IO. Here you can see Modbus TCP is the native protocol. So that's how the modules actually talk to each other. And then you have Profinet IO for Siemens devices, Ethernet IP, Allen Bradley devices. If you go into systems or change processors and things, sometimes, although it'll have a brand name on it, the actual programming software is CodeSys. If you have to use CodeSys, CodeSys has the ability to use all forms of communication. You just select how you want to connect, and our files work with CodeSys as well.
Oh, okay. Nice.
One item just to be aware of in case it ever comes up, when you use CodeSys, CodeSys expects ODVA firmware. So that would mean your current system could not use a CodeSys type of processor unless we upgrade all the modules and then upgrade make sure we use all the current files with the CodeSys system.
Gotcha.
You're going to hear me talk about assemblies. PLC mode, input assembly, output assembly. ZPA mode, input and output assemblies. And what we mean by an assembly is the module, the processor itself has 512 registers. All the data for the card is scattered throughout all of these registers. When you connect to a module, whether it's PLC or ZPA mode, the EDS file will then assemble in a known order and a known position the different information that's been scattered. So it'll collect it and assemble it in a known order. Then we can, since it's in a known order, we know exactly what information it is, and we can provide the files or the names of the register and what to expect from the input and what the output will actually do. If you use Modbus, we support service codes 3, 6, 16, and 23. Most of the time, customers are using 3 and 16 because they will allow you to either read write one register or multiple registers. So 3 and 16 are the most commonly used. Ethernet IP, Allen Bradley. Up here, you're going to have whatever name you used to when you created the module. Then :O for output dot data, then the index or array number. And then if that position actually has data to the bit level, then it would be .bit. Inputs and outputs are the same way. With Perfinet, we provide the DXML files and UDTs, and this will give you the same functionality as an EDS file with Allen Bradley. When we go through the charts, there's going to be 3 columns. On the very left over here will be the actual Modbus register number as it is in the processor. In the center will be all the connection information. So if I'm connecting with Modbus, it's going to be M, it's going to be green, and then it'll be 4 for Modbus, and then your address. Connecting with Ethernet IP, all the information is going to be red, E for Ethernet, data, and then array number. Anything related to Perfinet will be purple and P for Perfinet. Perfinet's always high byte, low byte. ZPA mode control. What all this is saying is with a PLC, you can now interlock/interface with the module. It will still perform the moving of loads from A to B all by itself, but we can interlock with it. We can change speeds. We can accumulate zones. We can write tracking data. We can read module and motor status, basic information, but the module itself is still controlling of the loads along the conveyor. Now this right here is just we have one for inputs and outputs as well. Starting at input data 0 all the way through input data 20, the register and the name of the register and what data it contains. So we will go ahead and we will start, and I will describe each register so you'll have an understanding of what it's providing.
Okay.
Notice here, hard register 116 is listed twice. Well, that's because this register is a high byte, low byte register. The low byte contains the status of the zone when the module is moving the load in the forward or your auto configured direction. The high byte of this integer would contain the zone status if the load is going in the reverse direction. If you use the EDS file and our add-on instruction, you don't have to worry about this. is when you open up the add-on instruction, it'll say zone status forward, zone status reverse. And you just look at the one for the direction you're going. You don't have to worry about masking out
Okay.
and doing all that math and thing. The add-on does that for you. So that is true for both the upstream and the downstream zone of the card. Now, yesterday we discussed how the cards, you heard me say this a bunch of times, they talk to each other.
Mm-hmm.
The biggest way they talk to each other is with these 5 values. 1, so if, for example, the downstream of node 1 is talking to the upstream of node 2.
Mm-hmm.
If it sends a 1, it's telling node 2, currently my sensor's clear and my motor is stopped. My zone is empty. If it sends a status of 2, that means my sensor is clear, but my motor is running. I'm accepting a load from node 1 upstream.
Okay.
Status 4, my sensor's blocked and my zone is running. That means I'm discharging to upstream of node 2. And when node 2 sees this, it will automatically turn on to accept the load. Our system would be considered a push. If upstream sees downstream is clear, we release with status 4. It's then up to downstream to turn on to accept and send status 2. I've just turned on to accept your load. So they're always talking back and forth.
Handshaking.
Yes. Status 5 means my sensor is blocked and my motor is stopped. My zone is accumulated. Status 6, busy. You'll see this 3 possible times. Number 1, when the cards first power up and they're doing that little search routine looking for a load between photo eyes, they will send status 6, I'm busy. If you turn on blink and wink, a feature that helps you find a module, that module will send its neighbors status 6. Right now I'm busy. And lastly, if you're using our convey stop software and it is active, the modules will send status 6. And I want you to see something. I always like to show this. So let's go to our programmers part of our calculator. Select a word. So here's our integer, 16 bits. And let's talk about zone status. Well, if you look at the raw data, not the value in the add-on instruction, but just, for example,
bit level.
We just look at input of register 116, the status for the upstream zone. If the zone, so we're going forward right now. If you look at the raw data, you're going to see a value of 257. Well, wait a minute. 257 isn't listed. Even though we're going forward, in the high byte, bit 8 will always be a 1. That's kind of some strange thing. I haven't questioned it because it's always been this way. So if we're in forward going and we're accepting 2, it'll show 258. The add-on instruction will mask out this high byte and show you a 2. If I'm discharging, the actual register will show 260, but in the add-on instruction, I mask this out. 4, discharging. So I like everybody to see this. So when they see strange values in the raw, if they look at the raw input data and wonder why those values are different than what's shown in the add-on instructions, It's because the add-on has some logic in it that does a lot of this work for you.
Mm-hmm.
The same thing is true if your conveyor is going reverse. Example, we're going reverse. It's going to show, and we're 1. It's still going to show 257. But now I'm accepting. Well, that's a 2 in the high byte. And you're going to see 513 in the raw data. I'm discharging. You're going to see 1025, 4 in the high byte. But because they always keep a bit as 1, that's what causes this strange value.
Mm-hmm.
But again, the add-on instruction takes care of all this. And what you would end up seeing in the tag is a 4.
Mm-hmm.
It would say upstream reverse status 4. So so automatic. So the add-on instruction will always give you the correct zone status no matter which direction you're going. Each zone has an arrival and departure counter. Block the eye, increment the arrival counter. Clear the eye, increment the departure counter. These go all the way up to 65, 535, and then flip back to 0. Also, a power cycle will clear these registers. Module status. It's pretty obvious that module status is this register, or these registers are all bitwise. So each bit has a meaning. So status word 1, input data 6, is mainly concerned with the left motor, but there is other information. So bit 0 is a 1 when the module resets. So you power cycle, bit 0 becomes a 1. If a PLC connects to that card, it becomes a 0. There are also other registers that are affected, but this is a really quick and easy way to determine as a PLC connected to this module. Bit 1 is a way to determine direction of flow. So if it's a 0, it means I'm going in my auto-configured direction forward. If it becomes a 1, that means something or someone has told this zone to go reverse. Bit 2, over voltage. Input power is over 30 volts. And this could be either from the power supply or the motor. Bit 3, left motor. If any bit 7, 8, or 10 through 14, which is this down here. Basically, bit 3 is just a general fault bit. It says, hey, there's a fault. Go look down here. I really don't use that bit because when I'm watching the cards and I'm looking for faults, I just look for the fault bits. I don't look for the general bit. So, but that's, excuse me, the purpose of that bit. 4, Ethernet connections not okay. Now that does not mean between the module and the PLC, because if that was true, how could the PLC see this bit turn on? What this means is, example, we're connected to node 2 and bit 4 turns on. That means it lost a connection to node 3 or to node 1. It's neighbors, not the PLC, but one of its assigned neighbors. Bit 5, upstream jam error. Now notice how everything else is left. That means physical. Bit 5 says upstream, so that's direction of flow. And that's a jam error. So that would be sensor jam. Bit 6.
That's an adjustable timer too, right?
Yes, that's your jam timers, yes. So by default, it's 5 seconds. You can crank it down to 0, which is not advisable because it would instantly jam, or you can crank it all the way up to 65 seconds.
Yeah, I thought I seen it in Easy Roll as an adjustable.
Yes. So that's under advanced dialogue, look ahead and timing, and it's your jam timers.
Mm-hmm.
And let me pull this over a little bit. So you can go from 1 to 65 seconds.
Okay.
Left sensor error. So that would be the gain, the pin 3 input on the sensor port. Using sensors from us, you will never see this because we don't use pin 3. Bit 7, low voltage, under 18 volts. Again, we learned that's important because we'll stop it. Motor control.
Mm-hmm.
Bit 8, the motor's overheated. The calculated temperature is 105 Celsius. If this happens, when the calculation says the motor has cooled down to 90 Celsius, it will continue operation or resume operation. Bit 9, overcurrent for the selected motor type, Eco, Boost, Boost 8. Yesterday, we talked about this one quite a bit, letting you know that it is normal to see this bit on startup and decel. I would not look at this as a fault. This is a condition.
Mm-hmm.
Short circuit, bit 10, that is a fault. Bit 11, motor not connected. So during auto configure, it detects a motor. Then somehow that motor is no longer detected. It's been unplugged, it's faulted some way. Bit 11 could turn on, not connected. Yes, that's a fault. Bit 12, the motor is overloaded. That means it's been stalled for 20 seconds. The motor will stop. The fault will clear after 60 seconds. This is a fault because the motor actually stops. Stalled, bit 13. I consider this a condition because the motor does not stop. It's just indicating that it's running at less than 10% of the set speed. Bit 14, Hall effect sensor error. Those are the positioning sensors. Yes, that is an error. If it has truly failed, the motor will no longer perform. It will be basically a paperweight trash.
Mm-hmm.
Bit 15, left motor not used. That means during auto configuration, a motor was not detected, so it's not being used. That is not a fault. So we get quite a bit of information in ZPA mode concerning motor and module status. Next, we have status word 2, input data 7. This is for the right motor. Bit 0, the reset or PLC connection tag or bit is not repeated. We do have the zone directional bit. We do have input power over 30, and that's because the right motor could be backfeeding over 30 volts. Bit 3 is the general error bit. Bit 4 is up here was an Ethernet connection bit. We don't need to repeat that. Bit 5, the downstream zone jam error. Then 6 through 15 is all right. The right sensor or error signal, right motor, low voltage. Bit 8, overheated. Bit 9, overcurrent. 10, short circuit. 11, motor not connected. 12, motor overloaded. 13, motor stalled. 14, right motor sensor error. And bit 15, the motor's not used. So they're exactly the same as the left motor, only this time it's the right motor. And again, all these bits correspond to these indicators in Easy Roll. So if you see these changing colors, it means that these bits are turning on. Tracking. Current tracking for upstream, we have 2 registers, and for downstream, it has 2 registers. You can combine these as one dent or use them as separate registers. If you use the add-on instruction, I followed the previous format, I guess, as my boss, and in the add-on instruction, provide tracking as a dent.
Okay.
The crazy thing is when I teach how to do tracking and write the tracking data, I take the dent apart into two integers, which means for ease, I should have just left it as two integers. I guess this was something that really wasn't thought out in the very beginning. And unfortunately, because I have just continued it, it's kind of the way it is. But knowing that, it's just a couple of instructions in Allen Bradley.
So it's two separate words.
Yes.
But
so what happens is in the actual tag in the add-on is a dent. So you can either write a big word, a big number, or you could, what we suggest, use two smaller numbers, one in the high word and one in the low word, which, comes back to the crazy part of, well, if you want to use them separately, why did you combine them? I don't know. Maybe the next release of the add-on, we have a little meeting with the global partners and say, is it okay if we separate this? Because that's how it's actually being used.
Right.
But for now, that's just how.
It combined them so you can have a bigger number?
Yes.
With the dent instead of the integer?
Yes.
I'm assuming.
Yes. Which really doesn't matter because you could still, if you had a big number, you could still combine it or separate it into the two dents. So I don't know. Either way, you'd have to do a little bit of Allen Bradley instructions. Neither one of is none of it's very complicated, and we'll see that today. Release counters for the upstream and a downstream zone. These I would consider these legacy, but they're still available. There's an output register. If the value in that output register is echoed in this input register, and it was a way to verify that, yes, the value I wrote to my output made it. By looking up here at the echo, it just mirrors what's in the output register.
Okay.
And we'll discuss what these actually do when we get down here to the outputs. Get tracking forward and get tracking reverse. Basically, the way the card handles tracking is we have a load at a sensor. That's the local tracking or at-eye tracking. The load releases and it goes to a temporary register. When the next sensor becomes blocked, that card will then look at that temporary register, grab that tracking data, whether it's a 0 or 57,000, whatever it is, and then it would be attached to that load. And if it releases, we'll show the tracking releases with it. And it does that on down the conveyor.
Okay, wait. Okay, this is the get tracking forward direction. We're 1 and 2.
Yeah. Well, we haven't really got to the get tracking yet. I wanted to give you a little explanation of how tracking works.
Right.
Okay,
Can we go back to the tracking and release tab 10.3.1.4? So upstream tracking, that's that value.
This value would be considered the at-eye. The load is here at the sensor, and this is the data for that load.
At whatever zone. Let's just say, say the first module, right? We just get a package, like one of the instances, like we're dealing with Coke products, right?
Okay. Yes.
They released us they got, so the way they're doing it is they have layers of product on a pallet. Each layer could be something different. if that makes any sense. So layer 1 could be 12-pack of Sprite. Layer 2 could be a 12-pack of Dr. Pepper or Coke or whatever. So when they start releasing that layer, top layer on that pallet, it could be 12 cases or 13 or whatever those cases is. But in order to identify them, you know, they use some kind of identifier as some, you know, I'm assuming a DIN or an integer as a value for tracking those packages, and then we typically have a counter eye that counts the packages before we know.
You've almost got our tracking down. You don't know it, but you're talking about how to do tracking with our product. You already understand it, but you don't know it yet.
No, I don't know it, but I just kind of got an idea of that product has to have an identifier that we can pull into this tracking for that when that package enters that zone.
Correct.
And then from that point on, ZPA would kind of handle from zone to zone.
That is correct.
I'm assuming, but anyway, okay, go ahead. I digress.
So you really understand it. What you don't know it yet. You'll realize it when I start showing programming examples.
Okay.
But you are correct. So these two right here is the current tracking at the sensor. The load has arrived. Now, when the sensor clears, it goes to a temporary register for holding. When the next sensor becomes blocked, it will look at that temporary register, get the tracking data, and now it's at the next eye with the load. And you can determine, oh, now this is load 57. Do I divert it or keep passing it? Okay, so it goes at eye to a temporary register, back to the next eye.
Okay,
so
hold on. All right, this is the good stuff. Hold on.
Okay.
So if I had three, let's just say we had 3 post rollers, 1, 2, 3, in that order, left to right, right?
Yes.
Zone 1 has an upstream and downstream.
Yes.
I just gotten the package from the layer 12-pack of Sprite. Identifier is 15. So we dump that into the tracking dent. When upstream gets ready to release to downstream and the sensor is flagged at downstream, it would transfer the tracking data 15, but you're saying that it goes into a holding register in between.
That is correct. That is
upstream to downstream, right?
That is correct. So this, is there a text? Here's my little text. So when the load's blocking the sensor, it's at the eye. When the sensor clears, so when this sensor clears, the tracking goes to that temporary register.
Okay, one second. So there's instances where upstream and downstream, the upstream sensor can be clear for a split moment before downstream is flagged.
That is correct, and it will be.
Okay, all right.
And at that point, at that point, this is where the tracking data goes. When this eye becomes blocked, it goes back here. Now it's at this eye, and I can read it. When this eye clears, The tracking goes to the next temporary register. And when this eye becomes blocked, this eye will read this register and grab all the data and move it here. At eye, temporary. When a load blocks the next eye, grab the data. I release it, put it in a temporary register. When this eye gets blocked, grab that data. And that's how it works along the conveyor.
Okay.
Now, these two temporary registers. That is what get forward and get reverse mean. So let's continue this. Okay. So I'm going to do another box. This is our last zone. When the last zone clears, the tracking data again is moved to a temporary register. But there's nothing to get the data. That's what get does. Get reads this temporary register from the very last zone. So if this had tracking data and you wanted to know what did I just release, I look at this register.
And then when I make
that register is get. That's what this get register's for.
And then I can make my diversion based upon that data after the last.
Yes. So this is the last zone. If you have a diverter in your conveyor, you would end up looking at the tracking for at I. I have this load. Do I divert it or pass it? And it's going to say divert or pass. If I pass, here goes the data. It goes to the next I. If I pass it and it's the last zone, it goes to this position. Now what happens? Now here comes another load. Temporary at I. Temporary at I. If it clears, it'll overwrite this data with the data from this load that's just released.
I got you. Okay.
Now the same thing is true if you're going reverse.
But the data, let's just say the data at get tracking forward, right?
Yes.
Word, I don't know what word that is. Is that word 1 or 2, or did they combine?
Yeah, so it's 2, and so you have a dent worth of data.
Oh, okay.
And all this data
is combined.
Is combined. That's what's here.
Okay, so let's just say that the package went and we went to the 2 temporaries, and then we transferred after the last module. Okay. I dumped it into get. I look at it. I make my diversion, right? Before my next package comes and overwrites my data.
Yes.
Can I override the data?
No.
I should just leave. There's no way for me to clear that register until the next package overwrites it.
That is correct. And the reason is this is an input register, which means the card is writing the value.
Okay. All right. So I got to know that. Okay. So if I'm going to do something diverting with that data, it has to be kind of like a one scan, one shot.
That's correct.
Because that data is going to be retained.
Only for one load. The next load is going to override it.
Correct. Okay.
So that's forward. Now this one, get tracking reverse, is the exact same, but we're going in the
right to left.
Yeah, so we're going in the opposite direction. So it would be when I release from this zone, it would go oop. It would go here. So this is get reverse, and this is get forward. Your sensor and control port inputs. Bit 0, left sensor port pin 3. Bit 1, left control port pin 3. 2 is a right sensor port pin 3. 3 is right control port pin 3. And then we have left sensor port pin 4, left control port pin 4, right sensor port pin 4, and right control port pin 4. Excuse me, all 8 of the control port and sensor port inputs.
Heartbeat.
Bit 15 is your heartbeat, on off. This comes in really handy for various things. It usually comes in the most handy when you're setting up Modbus communications. Modbus communications, your register sets can be 0 based or 1 based. And knowing the heartbeats in a known position, you could see if your registers line up correctly.
Okay.
Convey stop status. If you're using the convey stop software, it will let you know if there is a stop condition, and then per the bitwise, why the condition is present. It could be because of another module, lost connection with a module, lost connection from a PLC, because we can configure the modules to have stop and start buttons on them. It could be because of a stop button on the left or right control port, or it could be because the PLC issued a convey stop command.
Let's go back to the sensor and control ports. I'm a little confused, I gotta say. So,
okay,
let's talk one module upstream.
Yes.
Which would be left.
Okay.
Let's talk the sensor port pin 3 sensor. I think that's sensor port pin 4.
So bit 4, left sensor port pin 4. That would so that would turn on if the sensor in the left sensor port is energized.
Okay, so show me the module one more time. Show me a picture of the module so I can. I'm a little confused. I'm sorry.
So here's the sensor port. So here's the sensor port. And here's the LED. So in the left sensor port, if pin 4 is energized for the sensor, so left sensor port pin 4, bit 4 would be turned on in this register.
So we could have 2 sensors.
Yes, you actually can, yes. But
it's not practical, but I'm saying, like, you could have 2 sensors wired up to that one zone. That's what I'm getting at. That's what I'm saying.
That is correct. You could, but one of them in ZPA mode, pin 3 is just the health signal. So it really wouldn't have an effect on the zone operation. Only pin 4, the actual sensor.
In ZPA mode, sorry, pin 4 would be what we would look at to see if the sensor is present.
Yes.
Or if it's blocked. I'm saying if that upstream zone left conveyor or whatever you want is blocked. In ZPA mode, we would look at pin 4.
Yes.
Okay. And if we was in ZPA mode and pin 3
was on, that would mean the sensor health. The sensor is misaligned. The gain is set too high or too low.
Okay.
The one I skipped is called, it's reserved. It's reserved for reset protection. The way reset protection works is, one, you would have to create your module with the EDS file. There is a selection. You can have ZPA mode or PLC mode using reset protection. And what it does is, before a module will accept a command from the PLC, for example, force run a motor, change your speed, accumulate this zone, before it will accept those commands, it must be enabled to accept those commands. That's what reset protection does. When a card first powers up, there's two registers for reset protection, an input register, and there's also, oh, I don't know where they put it here. Right here. So output 18 reserved. This is part of reset protection. When a module powers up, input register 19 generates a random number. Guarantee it that it does not equal the output register.
Mm-hmm.
At that point, the module is not enabled to accept an output command from the PLC. Once you move this input 19 to output 18, and the firmware sees that the two registers have equal values, the module would then accept a command to force run. It would then accept the speed change. It would then accept the accumulation bit. There is this part right here is my personal opinion. I would only use reset protection if I have a module releasing to someone else's equipment. If our card is releasing to another one of our cards,
Mm-hmm.
there's no need for reset protection. The cards talk to each other and know if they can accept a load or not.
Mm-hmm.
In PLC mode, if a downstream piece of equipment is not ready, that would be one of the bit conditions in the motor run logic. Downstream must be ready. And if that's not on, you can't run the motor.
Right.
In ZPA mode, when you release to someone else's equipment, and this is how this feature came about. It's Monday morning, and you turn everything on. One switch turns everything on. You turn on your panel and your PLC. You turn on all the power supplies for the cards. And in this case, it also turned on a third-party taping machine. The PLC, it powers up. It's ready to go in a couple seconds. And so it writes to the card, accumulate. Well, the card's still powering up. It's going through its internal tasks. Okay, now I'm done. Open up communications and listen for my neighbors in a PLC. The problem is the card works on a change of state. And since the PLC wrote accumulate while the card was still starting up, the card did not see the accumulate bit. It has a load and it released. Well, the taping equipment downstream wasn't ready yet. It was still going through its startup cycle. And we were jamming it and causing issues and problems.
Mm-hmm.
And but the PLC said it accumulate. Why, what's going on here? Well, it was because of all the startup. PLC's faster than the cards. So what they developed was reset protection. And it requires 3 steps. Step 1. Let's say this is the card releasing to that taping equipment. In Easy Roll, you set accumulate. If you power cycle the card, this is saved to the flash memory. So the card will power up and accumulate. Perfect. That was step 1. So the last card powers up and accumulates, but does not release. Step 2. You must enable the part of the enable the card to accept output commands is downstream is ready. The taper is ready.
Mm-hmm.
Okay, now I can enable my card to accept an output command. Step 3. This accumulate bit or this accumulate button writes to the same bit the PLC writes to that says accumulate. So step 3 is turn on accumulation. And the card's going to say, oh, the PLC just told me to accumulate. That means the PLC is now in control of me. And then the PLC turns off accumulation and it allows the load to release to the taper. So reset protection is just an extra level of protection, ensuring that card control does not happen until it is absolutely ready. All the equipment is ready. This kind of helps prohibit the card from doing the release on its own. Because of the extra steps is why, my opinion is it's really only needed in ZPA mode if you are releasing to another piece of equipment that's not ours.
Gotcha.
Outputs. So here we just have just a straight listing of all the available output commands and features that we can control. Tracking. So each zone, upstream and downstream, has 2 registers, which means 32 bits of tracking data that we can track with the load. And you would just write it to these registers, or if you're using the add-on instruction, it's just one big tag it's a one big dent. Tracking details. What this is telling us, and I will show you this in a programming example today, is the cards, as you heard me already say this, the cards work on a change of state. And what this is telling us is that if we have 2 loads that have the exact same tracking data, example, load 1 shows up and we give it tracking data 5 to divert at lane 5. Release it, it goes to lane 5 and it diverts. The second load arrives. Oh, it goes to lane 5. Write value 5 and release the load. It goes to lane 5 and it keeps on going. Because the values were exactly the same, the second load received 0s for tracking data. There was no change. How do we overcome that? And this gets back to where you was already talking about this. We assign it a number. We give it something special to identify it. Well, then we take that dent, and in the low integer, we would write the divert lane. We would write 5. But in that high integer, when that first load arrived, we would increment, we call it a sequence number. So the first load arrives, the value becomes sequence 1. Put 1 in the high word, a 5 in the low word, release the load. Goes to lane 5 and diverts. The second load arrives, increment the counter. Now it's number 2. It goes to lane 5. Write that tracking data and release it. The load goes to lane 5 and diverts. Why? Because there was a change in the tracking data. It wasn't the exact same data every time. Well, then and then number 2, we can only pass numbers. We can't pass string data. Well, then how do I associate numbers and string data and all this other stuff in my PLC? I'll show you an example of that once we open up programming.
Okay.
And then you're probably thinking about it now, but once you kind of see some programming, it's going to make sense.
Okay.
Accumulation control. So this works for upstream zone or downstream zone. This register has a bitwise meaning. Bit 0 means accumulate the zone, whether it's the upstream or the downstream. I'll go to bit 8 last. I'll pull up the paint and explain it with paint. It's a lot easier. Bit 9 set the arrival confirmation for a zone. Yesterday, we heard me talking about when a zone releases, it wants confirmation or it will jam.
Mm-hmm.
Well, you divert a load off the conveyor. How can you confirm it diverted? You would energize bit 9. So if you divert from the upstream zone, when a load diverts, energize bit 9. Tell the zone the load made it. Give it the confirmation. Bits 10 and 11 are force jog, forward and reverse. So if your conveyor is full of product and you say force jog zone 8, well, if there's a load in zone 9, you're going to slam it right into zone 9 load. So this is force, no fault logic or anything involved. Bit 12, wake a zone up. So this could be zone 1, the very first zone. Instead of a wake up sensor, you just energize bit 12. Bit
what
13.
What does wake up actually do? Just
it wakes the zone. So yesterday we talked about you could use a wake up on the control port. Load comes from somebody else's equipment. It blocks our eye. The zone turns on to accept that load. You energized pin 4.
Okay.
Turning on bit 12 is the same thing. Only instead of having to use a hardwired photo eye, it would be a communications bit. No extra wiring involved.
So that zone just starts running.
Yeah, so this would just wake it up.
For a load.
Yep.
Okay.
The way bit 12 works, the way wake up works, whether it is a sensor or bit 12. You'd energize bit 12 or block the wake up eye. That zone will run, and it will run, and it will run until the zone becomes blocked and it, for some reason, has to accumulate.
Mm-hmm.
Or B, once you actually clear the eye or turn this bit off, the zone will continue to run for the jam time. So an easy roll, by default, the jam time is 5 seconds. So once we turn on wake up, the zone wakes up.
And we're waking up that zone, which is downstream.
Well, so you can wake up the upstream. If you write the output data 4, bit 12 wakes up the upstream. If you write the output data 5, bit 12, it would wake up the downstream.
Gotcha.
When you take that bit or signal away, that zone will continue to run until 1, the sensor becomes blocked, or 2, the jam timer expires, which is 5 seconds.
Okay.
Maintenance mode. You have to have a PLC to turn on maintenance mode. And what that does, I don't think, okay, wake up, firmware 4.1, so your 424 will do wake up. I don't think 424 will do maintenance mode. This is a more recent feature, but what that does is when you turn on bit 13, that side of the card, all the LEDs will start flashing green. That indicates maintenance mode.
Mm-hmm.
And as it says, maintenance. So a maintenance personnel could go to that card, that zone, replace a motor, O-bands, a sensor, and not have to worry about the motor running or loads from upstream entering that zone. It would just start force accumulating upstream. Yeah, it wouldn't sit. Normally, you'd have to unplug the card, and that would set PLC faults and other faults. This is just a way to keep the card powered, but suspend all motor commutation so you can work on it.
Okay.
Speed control. You can change the speed of the motors on the fly. Acceptable values, 1 to 1,000. 0. Remain at last non-zero value entered. that means this register is zero protected. And that's because not everybody will change speed with a PLC. They'll usually set it with easy roll and they're done. But when you connect with the PLC, unless you write a value in the register, it's going to be zero. Well, you don't want to write a zero speed. So that's why the register is zero protected. An example shows if you write a value of 400, that's interpreted as 40% speed. 1,000 would equal 100% speed.
Gotcha. Okay.
Release and accumulate on next for upstream and downstream zone. This right here, the release and accumulate register. These are outputs. We talked when we were talking about inputs, and I said current release count for upstream and downstream is an echo of the value in the output register. That's what these registers are. It's an echo of these values. And now the way these work, its intention was for tracking, but it can also, I found it very helpful for release from the very last zone of the conveyor. So the way this works is a couple steps. Step one, you would set the zone to always accumulate. When it comes to reading and writing tracking data, to accurately read and write tracking data, the zone must be accumulated. So that's why part of the reading or writing tracking data, step one, you have a rung with a coil that energizes the accumulate bit, and you always leave it on all the time. Step two, the load arrives. You can read the data or write data. When it comes time to release, that's when these registers come into play. Changing the value in the register would cause the current accumulated load to completely release and then accumulate the next load. So it's like a one-shot release. I have a load, I'm done with it, release it, and accumulate the next one. That's what these registers do. There's one for upstream and there's one for downstream. These will be used when you're doing tracking. Also, a good use for these I have found is the last zone in a conveyor. When the release from the last zone is dependent upon a signal from another piece of equipment. So part of your logic is one, always accumulate the last zone. Two, if I have a load and downstream's ready, energize the release bit or increment the counter. That load releases, the next one shows up. And if you could release as fast as they show up, then you will release as fast as they show up. But if you have to stop for some reason because the downstream equipment isn't ready, the load's just going to sit there because downstream's not ready yet. So these release and accumulate bits, one, are mandatory for tracking, but two, also come in handy for other parts of the conveyor.
Gotcha. Okay.
Status, set status for the upstream, which is inducting a load, or downstream, discharging a load. So these are for the very first zone in your conveyor and the very last zone in your conveyor, because they have no connection. Nobody else is talking to them, the first and the last zone. So the PLC can talk to them. And by writing the zone status values, 1, 2, 4, 5, or 6, you can wake up the upstream to accept the load, or you could force the last zone to accumulate and not release the load. So these two registers are for interlocking with the very first zone, induct, or the very last zone, the discharge zone. This induct status also works in conjunction with another command. One, you can just use it to wake the zone up, no problem. Write a value of 4, the zone's going to wake up, accept the load, and keep going. But induct tracking. So we have set induct tracking. Notice the word induct. We have induct status, and we have induct tracking. These will work together. So induct tracking. If you have tracking data, let's say your Coke is coming down a conveyor, and because it's on let's say, it's on some kind of belted conveyor, it's using an encoder, so it has tracking data for the loads, and we have a load coming off of your belt to our conveyor, and there's tracking data, and you want our cards to accept that data and pass it along with the load. Step 1, write the tracking data into these registers, set induct tracking. And again, this is just a tag in the add-on instruction. Step 2, write a value of 4 into the set status upstream induct. When you write a value of 4, that tells kind of fakes the card out. That tells the card, hey, upstream equipment is telling me to turn on to accept. It thinks it's another card. And because it thinks it's another card, this induct tracking, remember how we talked about get tracking and it was in a temporary register? Well, what we do is write the tracking into the temporary register. When the sensor becomes blocked, it automatically grabs it, keeps going. We don't have to accumulate, write, release. It's just a simple write the data, set status 4, and it happens automatically because it thinks it's coming from another card. Okay. And I can show an example of that if you'd like. And of course, if you're going in the reverse direction, you can induct tracking in the reverse direction as well. Clear motor error. The only error this will clear is a short circuit. So if you see the short circuit error, the bit turn on, you in output data 16 or a tag in the add-on, you would energize it, and here it lets you know 500 milliseconds, and then turn it off. Control port outputs. If in easy roll, advanced dialog control ports, if you select enable PLC to control a control port, you can energize these bits, bit 1 or bit 3, to actually turn on the control port output. Turning these on without that selection in easy roll, the card will ignore this command. Reserved. This was part of reset protection we talked about earlier. If you're using the convey stop software, if you want the PLC to set a stop command, you would write a 1 for 500 milliseconds and then write a 0. Convey stop means you have a group of cards. Group means at least 2. Let's say your group is a group of 50. Writing a command to just one module in the group will affect the entire group. So you don't have to write to every card, just one. So you would write a 1 for 500 milliseconds. That would set convey stop. Then write a 0, no more commands. When it's time to reset convey stop, write a 2 for 500 milliseconds, and then write a 0, no more commands. you must transition between a command and 0 where the module will ignore it. So if you write 1, set convey stop, and then write a 2, reset convey stop, it will ignore it because you didn't transition to 0 first. Jams. So in the motor, in the module status words for upstream and downstream, left, right, there was a bit, it was bit 5 that says there's a zone jam. And they're just transitioning the value in this register, changing it to a 1 and back to 0, clears the jam. It's the same as pressing the button in Easy Roll. Again, this is just a bit in the add-on instruction. These last two, I will discuss them, but they, unfortunately, because of your firmware, are inaccessible features at the moment. Accumulation, or it's called direction and accumulation mode, control for local upstream or downstream. These registers are very powerful. Number one, it's a high byte, low byte register. The low byte is a command. The high byte is starting with the zone you write to. So am I going to write the command to the upstream or the downstream zone? So starting with that zone, how many zones downstream, so it's a push, does this command affect? So for example, if we went to node 1 upstream, output data 22, and said command 5, run the motors. High byte, how many zones? 4. Enter. Well, that would run the motor, the 4 motors, node 1 upstream, downstream, node 2 upstream, downstream, 4 zones. It would force run them in the forward direction. Changing the command to 0, it would stop. Oh, that's pretty cool. Here comes the dangerous part. Right here. If you, in the high byte, if you say 0 zones, that means every zone. So if you had 50 cards and 100 motors, and you went to node 1 upstream and said command 5, number of zones 0, that would force run all 100 motors on your network. So this is a very powerful register and commands, because what you write in these registers can affect your entire conveyor. One thing to keep in mind, that these commands are ZPA commands. So in your 50 card network, card number 20 is in PLC mode. And you said node 1, command 5, run the motors, number of zones 0, meaning every zone. Enter. It would go all the way to card number 20, which is now PLC mode, and stop, because it's PLC mode. PLC mode does not accept ZPA commands or pass them through its registers downstream. And then lastly, convey merge. This was a feature we did not discuss, as I believe the firmware, you must have at least version 427 or newer for this feature. You can control how it works through this register. But with Easy Roll, for example, you would, let's say, in our example here, node 2. We have 2 spurs. So this is network 185. Let's say we're going to create a merger, and network 184 and 183 both merge into this module. Normally, you'd have to put these modules into PLC mode, or maybe leave them in ZPA mode. and you'd have to put all the programming into PLC. You would have to be traffic cop. You would have to control accumulation and release through the merger area. Well, what we did, you press control with, I know you can't see me do this, but first connect to the module that would be the master. Then press on your keyboard Control Shift M, M for merger. And you get a new dialog box. Enable the merger. And now we get a visual representation of what we're about to configure. So on the master card, you can merge into the upstream zone or the downstream zone. Not both. They can't be staggered, both in the same zone.
Mm-hmm.
Priority. First come, first serve. Center, left, or right has the priority. And then all you would do here is enter the IP address for this module right here. Enter the IP address of this module right here. Press apply. The software will take care of saying, merger master, you now talk upstream, downstream with this card, and you talk upstream, downstream with this card, plus this one here. So it makes all these special connections. And then it becomes traffic cop. And depending upon the loads coming here and block and photo eyes, it releases based upon the priority. First come, first serve, center, left, right.
Mm-hmm.
You can even have a T-merge. So if you have one lane coming in like this, you have all the settings to configure a T-merger.
Mm-hmm.
And that's why we have this register, the convey merge interface. And the reason for this is I'm the integrator, and I come over and you have beer, pop, and toilet paper running down 3 lines, and they're all going to one case stacker. So you can only send one product at a time. You can't mix them. Well, you could have different priorities. You could disable lines. Having this register and having this available on the HMI would then allow the customer to adjust the functionality of how the merger works without giving them the easy roll software and risking them going and changing all your settings on everything. And that would conclude yesterday's wrap up and just discussing ZPA control, interlock. Let's take our break. It's 10:30. Let's take a break till 10:45.
Okay.
We'll come back. We'll do PLC mode inputs and outputs and jump right into some programming examples. We'll start with that. I don't know what's in it. I haven't looked at it, but I still have that program I called Taylor when we were discussing some things a few weeks ago. And I'll just open that back up and we'll start putting examples, adding cards, all that kind of stuff into that program.
Okay.
And then like the simple little backups we've made, any programming that we do, I'll share all that with you when we're done.
That'd be great.
All right, so let's take our break and we'll come back at 10:45.
Okay, no problem.
All right, thank you. All right, are you with me, Tyler? Or Taylor, I'm sorry.
Yeah, I'm here.
All right. Let me open this back up. Find my share button. And okay. Ooh, I don't think I stopped the recording, so we'll have a 15-minute pause in that video. Sorry about that. So we'll begin here with PLC mode. In PLC mode, you have full control of the module. Inputs only have the meaning you give them, and motors only run when you tell them to. If a module is in PLC mode, you can still interface upstream and downstream with ZPA modules. It's just that in the PLC mode, you have full control. You have to manually pass status. It won't do it automatically. First part is you would connect with Easy Roll, select Advanced Dialog, Connections, and place the module into PLC mode. At this point, you can lock the module into PLC mode if you wish. Locking a module in PLC mode means that if you have to perform auto configure again, this module would remain in PLC mode. Usually it would go back to ZPA mode. So this is a way to keep it in PLC mode. Also in PLC mode, on PLC disconnect, outputs and motors. So if you lose your connection to the PLC, you want the motors and control port outputs to be all off or don't change. I'm a very big proponent of all off. No connection, all off. Clear connections. If you don't, notice how right now node 2 is still talking to node 1. If we clear connections, node 2 no longer talks to node 1. PLC program, what that is we offer our own programming software. Convey logics. This is from, as you can see, from a training a few weeks ago. And this is our programming software, free of charge. And as you can see, it's basically all the basic instructions. Wow, this looks like Allen Bradley ladder logic. And it does. I mean, you can write ladder programs and download it to the module, and the module will then work as a mini PLC. This is a way to maybe not have to buy an Allen Bradley PLC for thousands of dollars. You can put a couple of these programs in a couple of cards, and you're done. Depending on how you like to program, you can program in ladder logic, function block, and structured text. This software, there is a button here. I don't know if you can see that, but it says make a bin file. When it makes a bin file, that's what this is looking for. So if I'm going to go to a place where I know I have some ConveyLogix programs, let me see here. There we go. Notice how it's a bin file, but it begins with PLC data. That's what this is looking for. That's what that pop-up is saying. a bin file that begins with PLC data. And you could use that file and download the program with Easy Roll, or this also has a download button that you can download program, which you could download directly to the card. And so that's what this is for. So first you would place the module into PLC mode. We talked about clearing connections and what to do if the PLC loses connection. All off. PLC lock mode locks the module into PLC mode. Convey Logic's program. This is looking for a .bin file. Inputs. Now I want you to notice something. Earlier we talked about the assemblies and how the data is scattered throughout the registers, but in ZPA mode and PLC mode, we assemble those registers into known locations, and then we can access the data correctly. Something I'd like for you to see here is PLC mode inputs, sensor and control port inputs. The hard actual register on the processor is register 35. In ZPA mode, it's assembled in input data 1. In ZPA mode, the sensors, it's still registered 35, the exact same information, but it's assembled at input 18. So this is, I just wanted you to see this as an example of the assemblies and how things are assembled. They're not always assembled the same. They're just assembled in a known order. So convey stop, if you're using the software, it has the exact same bitwise information as it did in ZPA mode. Is either set by a communication loss, power loss, a push button, or a PLC. Sensor ports. The sensor port information is exactly the same, including the heartbeat. But now, because we're in PLC mode, we get more maybe diagnostic type of information. Example, sensor detect. This will detect if a sensor is connected to a sensor port. It does that by looking at the current draw between pins 2 and 5. If it sees current draw, it knows there's a sensor connected. Bit zero is for the right sensor, bit 1 is for the left sensor. So if you look at the register itself, you could see a decimal value of 0, 1, 2, or 3, depending on how these line up. Module voltage. The example says, if you see a value of 23,500, well, that's millivolts. Your voltage would be 23.5 volts. If you use the add-on instruction, I move this value into a real number and divide by 1,000. So you'll see 23 point or 24 point, whatever. It'll have the floating decimal. You'll see it in actual volts. Left motor current. Example, the register will be in milliamps. In the add-on instruction, I divide by 1,000 and put it in a real number with a floating decimal point, and I show amps. Frequency. This is just a straight value in hertz. If your motor is in eco mode, 483 hertz represents 100% speed. And it's not a solid, it'll bounce. It may say 481 to 485, bouncing right there. If your motors are in boost or boost 8 mode, 100% speed would be represented by 350 hertz. Motor temperature. This register is a high byte, low byte register. The high byte is the calculated motor temperature in Celsius. and the low byte is the actual temperature from a thermistor on the board. Motor status. Now again, it's bitwise. The important bits stay the same, but we have some new ones. Bit 0 and 1. They're read together, and they provide your rotational status. They're both a 0. The motor's not running, and braking is applied. Bit 0 is on. You're running counterclockwise. Bit 1 is on. You're running clockwise. Bit 1 and 0 are on. The motor is stopped with free brake applied. So these two are read together. Bit 2. The motor port is in digital mode. Yesterday, when we went through the tech specs, I briefly touched on an unused motor port can be used as 4 individual outputs. If you choose to do that, number one, you would set bit 15 in the motor in the digital output register. When you do that, bit 2 will turn on in the status register, letting you know that you have turned this into 4 outputs, not a motor controller. Bit 5 is a board overheat. This one's coming, the CPU itself has like an internal thermistor. That's what we're looking at. This will turn on at 140 Fahrenheit, 60 Celsius. It turns back off at 110 Fahrenheit. All this will do is indicate the board, the card is really hot. Your environment, your ambient temperature, plus the electronics has made this hot. Will it stop running the motors or stop communicating? No. It'll keep plugging and chugging as long as it can, but it will let you know I'm really hot. Bit 6, over voltage, over 30 volts. Bit 7, low voltage, under 18 volts. Overheated, 105 Celsius. Over current for the motor selection. Short circuit, motor not detected. Overloaded, stalled, sensor error, and motor not used. So here you can see these lower bits are the same whether you're in PLC mode or ZPA mode. The right motor. The exact same information is available, except it's in different registers. Current, frequency, temperatures, rotational, board, and motor status. Exactly the same. If you have placed your motor into digital mode, meaning it is now outputs, not motor controlling, and you've created a short circuit or you're drawing excessive current, these bit 12 will turn on in the status register for a short circuit, and bit 14 will turn on, letting you know you're drawing more than an amp across an output. Module status. Now, I want you to see, we'll go back to ZPA mode for a second. Here it says local status for the upstream zone and downstream zone. The local status, that means this card. In PLC mode, you know your status. It's in your program. You know if your motor's running. You know if your sensor's blocked. You know your status. What this says is upstream module status. So if your node 2 is in PLC mode and it says, and you look at this register and it says status 5, that means downstream of node 1 is accumulated. So this is the upstream module. Again, node 2 is in PLC mode and it says the downstream module status is a 5. that would mean node 3 upstream. That zone is accumulated. So this status is from the neighbor modules, not you specifically. You already know your status. Tracking. Tracking always goes downstream. So this is the tracking from the upstream module that's available for you now. So here's your tracking data. Reserved. This is part of the reset protection. And as we discussed earlier, I really don't think this is needed for PLC mode. It's just as easy for you to put in a bit that says downstream's not ready. This is a lot easier than having to go through the steps of reset protection. Servo status. Our motors and controllers are not stepper motors, servo motors, controllers in any way. But because we get feedback from the motor, we have servo type positioning and control. So left motor and right motor, this is the position of the motor from what would be its 0 point, its home. On a power cycle, the home position is always 0. If you're not using servo commands, all of this, it can be ignored. This is only if you're using the servo command capability. And because, like I said, we can read feedback from the sensors, we get pulses. So we know every time that Hall effect sensor clicks is a pulse.
How many pulses per revolution?
I knew you was going to ask that question. Yes, sir.
You knew I was going to ask, didn't you?
Let me see here. That is here. Motor pulse to distance calculation. You need to know the biggest thing you need to know is the speed code of your motor. And to find that, and I'll show you here. Let me pull up the tech specs here. Ordering information. So when you look at the end of your motor where the cable comes out, there's going to be a little round sticker. And you're going to see a part number that looks like this. Well, similar. It may not be this exact part number. But what you would want to look at is the speed code, the number before their last 4 letters. That's your speed code. The example or the motor in this example is a 60 speed code. So let's look at a 60 speed code. We would go to performance data for this, and we will find a 60 speed code. Speed code 60. A 60 speed code has a gear reduction of 11 to 1. A 35 speed code has a gear reduction of 55 thirds to 1, and so on. So 60 speed code, 11 to 1 gear reduction. So the calculation is pi times 48.6, the diameter of the motor, and this will give us the circumference. 11 is for the gear reduction. 30 is because we have 3 Hall effect sensors and 10 poles or 10 magnets. So 1 revolution of that motor without gearbox will produce 30 pulses. You multiply the pulses times the gear reduction, and then you have your pi times your diameter to give you your circumference.
Will your part number tell you the diameter?
Yes, it actually does. Yes. Let me see here. Part number. Right here. So PRAD 48. 48 means it's a 48.6 millimeter diameter tube.
Mm-hmm.
50 is a 50 millimeter diameter. These are the standard motor diameter tubes in Asia and Europe.
Mm-hmm.
60, this would be a pallet roller. So we have 60 and 63.5. So this number comes down here to your diameter. So yes, that is part of the part number. And so once we do the final calculation, we can see that there is, for a rotation of the motor, each pulse represents 0.463 millimeters of linear travel. That's a pretty good resolution for a conveyor motor, just to move a box.
Mm-hmm.
And this right here, because 50 pulses is the default decel distance. So if you have a 60 speed code motor with a 50 pulse decel, when it breaks the sensor and it's told to stop, it'll stop at a distance of 23 millimeters, basically 1 inch after blocking the eye.
Okay.
Mm-hmm. So that was silver positioning, and then status. This will let you know, have you told the motor to reset the position? Did you tell it to go somewhere, which is the command status of reset? If you turned on the output that says 0 the position, this bit would echo that. And in the output, if you say go to a position, this bit would become 0, meaning it's in process.
Gotcha.
Once it gets to the position, it will become a 1. I'm complete. I'm done. Outputs. Again, just a kind of straight listing of all the outputs. Now there's 27. Yep. 0 to 26. So there's 27 output registers. Again, convey stop if you're using that. Clear the motor error. Clears only a short circuit. Left and right motors in digital mode. So this is if you have a spare port, you can set that motor port to be 4 individual outputs. Step 1, energize bit 15. That turns digital output on. And then when you're ready to use the motor windings, energizing bit 0 is winding 3, bit 1 is winding 4, bit 2 is winding 5. Well, how do I know what wires and what windings, what am I turning on? You would go back up here to the motor ports. 3, 4, and 5 are the motor windings. And here you can see 3, 4, and 5 are gray, purple, and blue. Pretty simple. These won't change. Also, because we have the ability to control a brake, pin 9 is also an optional PNP output. And you can also enable that by saying turning on bit 6. Now there's one special feature. Let's say your motor port is controlling a motor, but it is not a brake motor. You still have the option of using pin 9. That's what bit 7's for. If you are still using a motor, but it's not a brake motor, turn on bit 7. That means allow me to control the brake output. And then turning bit 6 on and off would turn on a PNP output, peaking at an amp, rated at half amp current. Again, this is the same for both the left and right motors. Control port output. Bit 1 turns the left control port output on. Bit 3 turns the right output on. Motor control. Bit 0 means run the motor. Bit 8 means change direction. So if an easy roll, the direction is clockwise. When you turn on bit 0, it'll run clockwise. If you turn on bit 8 and 0, meaning change direction and run, it would then run counterclockwise. The brake method, this can be set by easy roll or changed on the fly with easy roll, or I'm sorry, with a PLC command. I've not seen too many people do this, but the option is available. Speed control. This is a high byte, low byte register. In your case, because of the firmware 424, the only part that will apply to you is the low byte, being able to turn a motor, the open and closed loop on and off. The high byte for special motor slaving features, here it lets you know you have to have firmware 427 or newer. So this would not apply to you. Your speed reference, just like ZPA, same values. Example, 400 equals 40%. Your accel and decel values, you can adjust these. If your motor is an open loop, the time you enter is in milliseconds. If your motor is in closed loop, the value you enter is in motor pulses. Right motor control is the exact same as the left, they're just different registers. Same kind of control. Run, direction, braking, open, closed loop, speeds, accels, and decels. Just as we had status from the upstream module and from the downstream module, we also have the ability to set status to downstream and to upstream. So this is what we write to the neighbor cards. This is my status. Tracking. If this PLC mode module has a load with tracking data, and we want to release the load with the tracking data, first we would write the value of the tracking value in the tracking register, and then release the load. Reserved, again, this is part of the reset protection. Sensor port and the control port masking. What this does, it gives you access to each pin or each input, and you can invert the state. Do you have to? No. Sometimes it usually comes down to programming preferences. An example would be, let me just start a quick program here. With the photo eyes that we sell, a blocked, this equals the block state. And this equals the clear state of the input. Lots of times people would want this to be the block state and this to be the clear state, because that's their programming style. That's what they're always used to seeing. Well, all you would then do is, for example, left sensor port pin 4. You would energize bit 4. That would invert the state, thereby making the logic you're used to, normally open when energized, is now blocked. So all these do is invert the state of the input signal. Servo control. Again, okay, wow, they did put it in early. It's in firmware 4.14, so if you choose to use some kind of servo controlling, it will be available to you. And the command works. Only 2 bits are used. Bit 0 means reset the position to position 0. For example, you have a pop-up transfer and you're doing your homing routine. When I find the down procs, energize bit 0. 0 my position. Home is 0. Bit 1 is the go command. Go, run. Well, what happens when I press this? Well, the card looks at the pulses, command pulses. This is where do I go to? So I would enter a value of 100, go. And it would go from, in relationship to position 0, the motor would go to position 100, 100 pulses. Our servo control and retention of home position and where I am is very, very good. You can go between points. You can, home once a day, once a week, and then say go to all these various positions in relationship to the home position. And it will. I have a demo out here that shows that. It's very good. When you're looking at the registers, the values, the actual register, because it's an integer, will go from negative 32,767 to 0 up to 32,767. When it gets to 32,768, it actually flips back over to negative 32,767. And that would be the output side or portion of the ERSC and PLC mode. Do you have any questions?
No, not at the moment.
Okay. We have our section connecting to Rockwell PLCs. It does discuss how to use a generic Ethernet instance. And there's a little video that shows you how to create the module with a generic instance. A procedure for using the EDS file. So there's a video for reference. And of course, add-on instruction, using the add-on instruction, and a video for reference. We're not going to use the videos. We're going to use me. We're going to do this live.
Okay.
Tag descriptions for the add-on instructions. Some of the tag, the way the tag is named, may have slightly changed, but the meaning is still the same.
Okay.
I'm where an example could be where the previous add-on instruction said status upstream zone, fully written out. The new tag may say STS for status, underscore up for upstream, and then ZN for zone. So it made it shorter, makes the tags information a little bit more tighter, cleaner looking in your program, but it would be the exact same thing, status of the upstream zone. And down here, we have, if you would like to use message instructions, this is an excellent way to read data from a module without having to add it to your IO tree. We have, examples of how to read register. So this would be a read register of register 88. This is the PLC mode motor status register. So this is just this example. And you can also do write instructions. This is an example of setting the speed of the left motor. So we can now begin. If you have no questions. I thought I had that open already. My mistake. Go to your folder. There we go. Question: do you know what version software you're running?
In Studio 5000?
Are you using Studio 5000 or Logix 5000?
Studio. That's fine. B35 is
35 is okay?
Yeah, that's fine. Yeah, well, I think we're running 30. It'd be 34 up to 36, but 35 should be okay.
35 is okay, perfect. Because my processor's set at 35, so we can go online.
Yeah, that's fine.
Okay, so you can see we've already kind of started here, but we'll kind of redo this. I believe this is from our first session. We kind of discussed some of this, but we'll go ahead and redo it. So first thing that we did was we went to our downloads on the Pulse Roller website, controllers, convey links, PLC connectivity, Ethernet IP files, and yours would be previous versions. And you would have for version 424 and older. Yeah. I can't put that in mind without deleting things.
Yeah. What firmware are you running now?
I'm sorry?
What firmware do you have installed?
I'm actually running the 5 series, the latest and greatest stuff.
So you installed the EDS file for the 5 series?
Yes.
That's fine if you want
to. Okay. So it's basically tools, the EDS hardware installation tool for the wizard. Next, register. Next, then of course browse. And yours will probably look like these: a ZPA and a PLC IO, or possibly this one. They didn't start becoming combined until we got up into the newer series here. So some of these originals are the firmware 424 stuff. So you would have a separate ZPA and PLC mode EDS file. But basically, this is our latest EDS file. Open. Next. Yes. Install. Yes. And we'll see how, well, that's quick. Then you would just select new module. Make sure if it says hide filters, just show filters. Uncheck the vendors and scroll to Insight. And then all the EDS files for us are now available. Here you can see I actually do have one, the ZPA for 420 firmware 424. I actually do have that. So this would be one you would select. For purposes of today, it's going to be the standard, this one. That's how these are made. So we selected this one. And then when we did, we got this page. We gave it a name, give it an IP address. Next, and this is in the video, select change. Do not press OK. Not yet. Go to change. This is where you select how to use the module. I don't think with your version you have the selection because it's either ZPA or PLC mode. Be sure under size, you select integer. You could either use compatible module or disable the keying. Then you can press OK. Yes. Now you can press OK here. If you forgot, let's say you pressed OK and it closed. Oh, wait a minute. I forgot to change this to an integer. Then you go back and do it after pressing this OK. It won't work. You'll have to actually delete this module and then recreate it. Now, I always say that because that is for sure going to work. Depending on your processor and which version of Studio you're using, I've seen different results. Result number one, just changing from after you create it, you made the mistake. You go back and go from short integer to integer and press OK. Some processors will not update the data type in the controller tags. Let's say, for example, short integer will create the module with data type A. The add-on instruction is looking for data type G. If you go in and change the data type after you create it, some processors will, even though you went to an integer, will keep data type A. Some processors will actually change it and upgrade it to data type G. I don't know what ranges, which processors, what versions, that I don't know. But I do know that if you delete it and recreate it, that will work for sure.
Okay.
And now that we have our modules created, we can then import our add-on instructions. So it'd be right-click and import. And we would go to where we save our add-on instructions. And again, I believe I talked about why I lock them and don't put them out unlocked. And here you can see I have, these are all the ones that I've worked with. So these are ones that I've actually made. And we would select the ERSC for firmware 43510 and _1. I'd have to look at the revision notes I put on it to see what little bug I found in my programming. And of course, the ERSC PLC mode as well. And we would just import these. Let's say we'll go ahead and do it anyway here. Open. And it's just like, no, it's already there. If we import it, it would just override. Okay. No big deal. If we open it up, we'll look at parameters, which is the wrong one. Here we go. This is the tab I wanted. So for major 2, extended 2. So we go to see what's, so that's extended text 1. Corrected the right server position input. And this would be text 2. I corrected some descriptions in the motor status for the right word. I guess I had some typos with the words, so I corrected them. So nobody's perfect. I'm not ashamed to admit that. And if I have to do a minor bug fix, you know, this one I should have added text 2, like here I added text 1. So now we have created modules in our IO tree, and we have imported the add-on instructions. I'd like to discuss another oddity with the AB software. Again, I don't know which studio versions this applies to or which processors this applies to. But I have found that in some of them, You cannot import the add-on instruction until you have actually created the module in the IO tree. And when you try to do it, you'll get the error that says data type not present, meaning when you create a module, it creates a data type that the add-on instruction is looking for, and that data type wasn't present. So that's why I believe the documentation was updated. But when I discuss this, in the PLC section, that's why I always go ahead and add these first, because some processors require that. And let me see how I have node 2 created. Okay, it too is in ZPA mode for now, which is perfect. Main program. So we've already done some of this already. We had our main logic. I always like to grab a system first scan bit in case I want to use it somewhere. The module mapping. This is where we added our add-on instruction to a run, gave it a name. Again, personal preference. I like to name the add-on the same as the module in the IO tree, because I believe we talked about this when we hit the drop downs. If we had 100 modules, this would be node 1 through 100, and they'd all be listed because they all have the same data type. If you give it a custom name, you're going to have yourself some kind of a spreadsheet as a cross-reference to know this fancy name is really node 1 and requires the node 1 inputs and outputs. That's why personal preference, leave all these the same name. And then we did the basics. Understanding the tracking part. If you can understand this, the rest of the cards and reading, writing, all that stuff should be fairly simple. So as we did the first time, tracking. Always accumulate to write tracking. So we're going to write tracking data on node 1 downstream. Step 2, when a load arrives, increment a sequence number. That way that guarantees the change of state. And we talked about this, or we've been talking about this. And all I'm doing here with this little run is making sure that my number does not get too large. If you're doing 10,000 loads a day, yours is going to be 10,001. So you can have an array from 0 to 10,000, and you can track all 10,000 packages.
So node 1 has an arrival bit to the package.
Yes.
There. That's bit.
Well, this is not a bit. This is a bit that says accumulate. But this arrival for this to turn on, downstream zone. So in order for the arrival bit to turn on, 1, you have to tell it to accumulate. That's what this bit is. And 2, I have to have zone status 5. The motor stopped and the sensor blocked. So if it is stopped and blocked, because I forced it to accumulate, turn on the arrival. That's when this would turn on. That's when we would increment our sequence number. Again, the load arrived, and I put this testing bit in here so we could delay all the logic and watch it work. For tracking. So if we go into our add-on instruction for node 1, opens up, I for input, underscore, and then you have, then it's in alphabetical order, all your options. So here's the arrival in the downstream zone. And way down here under outputs, tracking for the downstream zone. And that's where we're going to write our tracking data. And because this is a dent, and we're going to write 2 pieces of information in there, we need to put it in the correct position. The sequence number, we're going to put in the high side. So the sequence number is going here in the high side. The divert location is going down here in the lower. So although this is one big dent, we're putting in 2 pieces of information. And then we release the load. To read the data, again, accumulate the zone. When we have the arrival, we can take our tracking apart. Again, this is a dent. And where we multiplied to put it in for the sequence number, well, we divide to take the sequence number out. And we still use a mask move. We used a mask move to put the location in. Then we'll use a mask move to pull the location back out. And then based upon your tracking information, do we divert here or do we bypass the load? If we, this step right here where we're looking at the tracking from the upstream, we don't have to move it to the downstream. That will happen automatically because they're in ZPA and they're talking to each other.
Right.
So again, so this would be the basic. And I think we kind of, we went through this. That's why we have actual real numbers and things in here.
So that tracking upstream is going to get automatically updated.
That is correct.
Downstream of the previous model.
That is correct.
And then so you divide, I think it's in hex.
Yes, this is in hex.
And you
divide, this is hex. And we divide since this is a dent, I believe this value is 256.
So really you're getting the top half?
Yeah. So all I'm doing is getting the top half and putting that value into the sequence number. Yeah.
Okay, and then the bottom half, you're actually putting the
divert location, lane 5, lane 10, lane whichever.
Whatever that number is, the divert.
Yeah. That is correct. And I don't know if we went as far as, let me see. Yeah, so tracking. You see how deep did we actually go into tracking? Perfect. So we did kind of do this a little bit. So then it's, well, what does sequence number 1 mean? That really tells me nothing other than it's sequence. Well, we created a UDT. We called it tracking. And we put in carrier. So this would be, it'd go to the warehouse system and it would come back and tell you, well, this is a UPS load. Address. 2748 Circle Port Drive, Erlanger, Kentucky 41018. That's our address. And that's where it's shipping to. And although we're only tracking a number, that number in the PLC represents a UPS load coming to our office. So that's a way to use that sequence number to get all this real information. And of course, when you create something like this tracking UDT, you can, of course, have any fields you want, strings, numbers, whatever. And then it's just up to you to then grab that data from the warehouse system, populate these points before you release the load.
Okay.
So that would, for example, so that would be something like before we would release, You would end up would be, because it's string, insert copy, enter, new tag. I'm gonna call this I don't even know what they call warehouse systems anymore. So it's coming from the warehouse.
WCS.
There you go, WCS.
I think they call it. They got these different warehouse systems, which to me, I guess they're just big old databases, really, from what you can query data out. But yeah, they WCS or something like that.
So this would be make sure I did make it a string. So this would be the string shipper. The destination would end up being destination.
Maybe it'll be in the tracking.
Yeah, so it'd be destination, tracking, length. The length is the length of the original tag. But I said tracking 1. Well, that would always go to tracking 1. Where does it actually go? To the position of the sequence number. So this would actually end up writing UPS to the carrier position at the second one. Does that make sense? How I'm getting to the so that's how this would then all come into play.
Tracking word 1, 0, 1 if the sequence is indirect.
Yeah. So right now we're at sequence 2. So then this information would go into sequence number 2 at the carrier. So that's how all this kind of works together, how to use a sequence number to fulfill our requirements of numbers only, and something has to change, and then applying it towards real world, an Allen Bradley project, and tags with real meaning, real information.
Gotcha.
Tell you what, it's 11:45. We've made a lot of progress. We've already kind of retouched on this, the basic program, being able to create the modules, import add-on instructions. And what I always like to do is the tracking part, being able to accumulate a load, determine the loads arrived, increment sequence numbers, write the data, and release it. We added just a little bit because we did the UDT to specialize our tracking information, and also added a little rung to show how to then move warehouse information into our tracking array so that our sequence number has meaningful information.
Gotcha.
Let's break for lunch. We can come back whenever you'd like.
Okay.
And if you have no more ZPA kind of related questions, we'll step right over into the PLC side and show how to do PLC control and how to handshake status and information between a PLC card and a ZPA card.
Yeah, that'd be great. Yeah, I'm sure I have some more questions for ZPA.
Oh, sure. Okay, we'll do that first.
I definitely got to understand the relationship of transfer and tracking data.
Okay.
And I think this is a great example, but I want to make sure that I cover all of the tag. I want to look at the tag structure now in the PLC, the inputs, outputs. Not now, but at 1 o'clock where we were being.
Okay.
And then we'll talk through some of those tags, and I'll make sure we reference back to the manual as to the right functionality, so I can understand
where it's coming from. Yes.
Yeah, and how to manipulate it in ZPA mode versus PLC mode, because we do track product.
Okay, you do track your product.
Tracking is going to be a big The merge, I'm not so sure, but there is some merge functionality that you show me within your software, so that should take care of the basic merge that we have. But for the most part, it's I'm getting the information from WCS, and I need to be able to track it along, the zones. That's like one of my main concerns.
That's exactly what we just did with these read and write tracking data.
Yep.
These simple rungs. So that's 1, 2. So we have 4 rungs to accumulate and write, and 2 rungs to accumulate, read, and make a decision.
Okay. Yeah. We'll come back and revisit this, I guess. I'm sure. Give me a moment to gather my questions.
Of course. Yeah. I understand this is a whole lot of information. So, develop your thoughts, write down your questions, and I'll be sure to cover everything.
Okay. Yeah. And we'll reconvene, I guess, at 1. Make sure to
stop the recording.
Yeah, because it'll be a long video for the guys.